have n is equal to 1. Here we have n is equal to 2. Right? We keep going on in this manner. I'm going to go ahead and write the n minus first term. So we get here alpha minus 1 plus f of alpha minus 1 plus 1, so just f of alpha. So here n is equal to alpha minus 1. Right? And then our last term, our nth term, our alpha term would be f of alpha minus f of alpha plus 1, like this. Right, so this is the n equals alpha term. So what we notice here, actually I made a tiny little mistake here. This should be f of alpha minus 1 minus f of alpha. These should all be a minus sign. Right, what we notice here is that if we actually were to separate all these brackets, what we end up getting would be the f of minus 1, not minus 1, that's a lie, just f of 1. So we get f of 1 minus f of 2. Now we get plus f of 2 minus f of 3. And if we were to write the next term out, we would get plus an f of 3. And we continue on this way until in our last two terms we get f of alpha minus 1 positive minus f of alpha plus f of alpha minus f of alpha plus 1, right? Now, if we just put convenient brackets here, so we'll put a plus minus f of 2 plus f of 2, we'll put another plus here, brackets, minus f of 3 plus f of 3, and we can actually even go ahead and write in the minus f of alpha minus 1 that we get here. All right, so we have plus this, and we get a plus this. Well, all these terms, we can see that all these terms here are equal to 0. Right? F of 3 minus f of 3 is 0. F of 2 minus f of 2 is 0. F of alpha minus 1 minus f of alpha minus 1 is 0. F of alpha minus f of alpha is 0. So this is all just going to, all these inner terms are going to cancel out, and what we're going to be left off with is just f of 1 minus f of alpha plus 1. Right? So this is going to be really useful to solve some particular types of series, and these types of series are called telescoping series. So this method is called the method of differences. And the type of series isn't important for the FP2 exam, but the type of series is telescoping. So type of series is telescoping. Okay, so let's continue on. Let's make a new page. I'll just get rid of everything on this page. Okay, so let's try a specific example. Let's try to find the sum of the series 1 over n. We're going to start basic. Minus 1 over n plus 1. And to make things a little bit more interesting, I guess, we'll say, let's take, that doesn't make any sense. Let's take the bottom value to be 1, so our lower index to be 1, and we want to sum this up to infinity. All right, well, the infinity, we're going to just not worry about it for right now. So we'll say, call this alpha. So what we actually really first want to find is the limit as n goes from 1 to alpha of 1 over n minus 1 over n plus 1. Right? Well, let's write this out term for term. Term for term, this would give us 1 over 1 minus 1 over 2, right? Plus our second term, 1 over 2 minus 1 over 3, plus, we'll do one more, just to make it really obvious, 1 over 3 minus 1 over 4. Then we'll do plus dot dot dot, our second to last term is going to be when alpha is equal to minus 1, so we get 1 over alpha minus 1 minus 1 over alpha, right? Alpha minus 1 plus 1 is just alpha. And our last term would just be 1 over alpha minus 1 over alpha plus 1. Right, so this is almost exactly what we have in our general case. Now, I'm not going to rearrange all these parentheses because it's not really all that necessary here, because all we're doing is we're adding. But I am going to now cancel out all these inner terms, right? The 1/2 and the minus 1/2 cancel. The minus 1/3 and the 1/3 cancel. The minus 1/4 is going to cancel with a 1/4. It's going to be over here somewhere. This alpha minus 1 is going to cancel with an alpha minus 1. It's going to be over here somewhere. Minus 1 over alpha is going to cancel with this positive 1 over alpha. And what we're going to be left over with is 1 minus 1 over alpha plus 1. Now, this is just the alpha partial sum, right? So we haven't actually calculated as we go to infinity. All we have to do now to find the infinite sum, and so got the infinite sum of 1 over n minus 1 over n plus 1, is just consider, and this is fancy notation that you guys don't use in EDEXCEL, but you've done it, you've probably seen it before. So all we have to do is consider now the limit as alpha goes to infinity of this thing that we've done here. It's 1 minus 1 over alpha plus 1. Well, this is actually really simple. If we divide by something that's getting larger and larger and larger, well, this thing gets smaller and smaller, it goes to 0, and what we're left over with is just 1. So this is a fairly basic problem. Let's try one that's a little bit more complicated. So we're going to say we've got the series. Let's see. We'll do really not that much more complicated. They all end up being sort of similar. So we'll do e to the I minus e to the I. We'll try minus 1. We'll see what happens when we do this. So we'll start from I is equal to 0, and we'll just go to some integer n. Doesn't matter what that integer is. So again, as we would do for most of these problems, we're going to start by just plugging in numbers. So our first term is going to give us e to the 0 minus e to the minus 1. Right? Our next term is going to give us e to the 1 minus e to the 0. Right? Next term is going to give us e to the 2 minus e to the 1. One more, e to the 3 minus e to the 2. And then we're going to keep going. We're going to write our n minus first term, which would be e to the n minus 1 here, minus e to the n minus 1 minus 1 is n minus 2. Our nth term is going to be e to the n minus e to the n minus 1. Right? I'm actually going to go ahead and just write one more term here just to be 100% sure that we know what we're doing. This is going to be our n minus 2 case, so this will be n minus 2 here. I'll have an e to the n minus 3 here. Okay, so now we got to see which terms cancel. Well, e0's clearly cancel, right? E1's clearly cancel. E2's clearly cancel. E3's clearly cancel. En minus 2's clearly cancel. En minus 3's clearly cancel. Oops, I canceled the wrong e. Well, that's an n minus 1, but it's also going to cancel with this n minus 1, so it doesn't matter. So it looks like what we're left over with is just e to the n minus e to the minus 1, which is another way of saying e to the n minus 1 over e. Right, and that's it. There's nothing nothing too complicated about this. So if we were to say, what's the infinite limit here? So if we were to say, what's the sum as this thing goes to infinity? What's the sum as this thing goes to infinity? Well, it's just the limit. I know that you're not necessarily used to these limit notations, but just the limit as n goes to infinity of e to the n minus 1 over e. right? Well, this is clearly infinity, right? E to the infinity, e raised to some power, as that power gets bigger and bigger, blows up. So this whole thing blows up to infinity. So we'd say this particular series doesn't converge. So let's see a particular reason why this sort of method is useful. Something that you've taken for granted in earlier modules. So in FP1, you took for granted the fact that the sum of r cubed, I think you guys used r, as r went from 0 or 1 or 0 to some finite integer n, was equal to n squared n plus 1 squared over 4. For example, I mean there are more here than just this one, but this is an example of one that you use. Well, now we can prove it, right? And the good thing is that in FP2 you're not going to be expected to come up with any of these formulas that you're going to need for these proofs, but there are various formulas that can be derived to help prove this sort of thing. So what we're going to be doing is we're going to be saying we want to prove this sum right here. We want to prove this formula by using the fact that 4r to the power of 3 is equal to r squared times 1 plus r all squared minus 1 minus r all squared r squared. That's not the exact format that we wanted though. What we want is r squared r plus 1 squared minus r minus 1, right, squared. We can change this because multiplying by minus 1 on the inside of a square doesn't actually change the value of the square. So these two things are exactly equivalent. So the first thing we want to do is we want to show that this is actually true. We want to show that this actually does expand to 4r cubed. So let's do that. So how do we expand r squared times r plus 1 squared minus r minus 1 squared times r squared? Well, simple. We say this is equal to r squared times r squared plus 2r plus 1 minus, now we expand this thing here, minus brackets r squared minus 2r plus 1 times r squared. Now we just simply expand the brackets and sum up and subtract like terms. So here we get r to the 4th plus 2r to the 3rd plus r squared. And here we get minus r to the 4th plus 2r to the 3rd minus r squared. Okay, so here we can clearly see that these r squareds cancel. The r to the 4th canceled, and what we end up with is 2 plus 2, which is 4 r cubed. Okay, so whether or not you see where this formula comes from doesn't really matter. The fact of the matter, the only thing that does matter is that this actually, when you expand it, does equal to this 4r cubed thing. And in an FP2 exam, you're going to be given these formulas. They won't ever expect you to come up with these formulas on your own. So let's see. I'm gonna get rid of this stuff. We've proven to ourselves that that's true. And we're going to try and prove this formula here using the fact that this is equal to 4r cubed. So first and foremost, if we had the sum of 4r cubed, if we knew what this was equal to, how can we find the sum of r cubed? Well, we know that the sum is what we call a linear operator, so we can actually take out constants, right? It's sort of like, remember, sums are basically, or integrals are basically sums. We could do it with integrals, so this is a way to remember it. I mean, it's not the reason why, but the way to remember it. So we could take that 4 out immediately from the sum and get that 4 times the sum of r cubed from r equals 1 to n is the exact same thing as the sum of 4r cubed, which is great because if we find out 4r cubed, all we have to do is divide whatever we come up with for 4r cubed by 4, and we'll get our answer for the sum of r cubed, which is already a good sign because we have a 4 in the denominator here in our actual the formula that we want to come up with. So let's go ahead and try and do it. So the sum of 4r cubed, since 4r cubed is equal to this, is clearly also equal to the sum of r squared, r plus 1 quantity squared, minus r minus 1 quantity squared, r squared, from r equals 1 to n, right? So what happens here? Let's write this out term for term. What's our first term going to give us? Well, let's just plug in 1 for r. So we get 1 times 1 plus 1, which is 2, squared. So this first term would be 4. We get 4. Here we get 1 minus 1 is 0, so we already know that that's 0. So we'd be subtracting off 0 as our first term. Our second term would be plug in 2. So here we get 2 squared, which is 4, times 2 plus 1 is 3, squared is 9. So 4 times 3, 4 times 9, which is 36. Our next term would be plugging in 2 here. We get 1 times 4 squared, so minus 4. Right? You following me so far? So all I've done here is I plugged in 1 to this, and then I plugged in, so that was this first term, so this is when r is equal to 1. This is when r is equal to 2. Looks like an n. R. Right, so let's maybe do one more. So r is equal to 3. We get 9 times 4 squared, which is 9 times 16, which is 90 plus 54, so 144. Hope I did that right. And that plugging in r equals 3 here, we'd get 2 squared times 3 squared, which we already did in a previous one. It's 36, so minus 36. Doesn't really matter if I get this 144 right or not, although I'm pretty sure I did, because this is already looking sort of like the method of differences, and we know that this 144 is going to cancel out somewhere else. Okay, so let's write our last two terms. So our second to last term is, let's see, n minus 1 quantity squared times n squared, right? Plugging in n minus 1 here gives us n minus 1 plus 1 is n. Right? Then we're going to be subtracting off, plugging n minus 1 to r minus 1 is n minus 2 squared times n minus 1 squared. Right? This is our second to last term. Our last term is going to be, let's see, n squared times n plus 1 squared minus n minus 1 squared times n squared. Okay, so now let's see which terms cancel. Well, 0 goes away. It doesn't have to cancel. 4 cancels with minus 4. This 36 cancels with minus 36. 144 is going to cancel with minus 144 over there. This minus this n minus 1 squared n squared is going to cancel with this minus n minus 1 squared n squared over here. The same thing is going to happen for this in the previous term. And what we're going to be left up with is just n squared, n plus 1 squared, right? Which is good, because we know that this is equal to the sum of 4r cubed, right, as r goes from 1 to n, which is also equal to 4 times the sum of r cubed from 1 to n. And so therefore, the sum of r cubed from 1 to n is just equal to, well, this thing here divided by 4. So n squared, n plus 1 squared divided by 4. Well, that's exactly what we wanted, right? It's the exact same thing that we had up here. So we have a check mark. So good, we've done well. Right, so let's try a slightly more difficult example, and then we'll call it a day for the subject. So we are going to want to find the sum of, let's see, let's do a good one. 1 divided by, you know what, I'm actually going to just use a common one. It's not that difficult, actually, but it's just to help remind us of a certain technique that we did in C3. So I think this one's actually in the book. that we're going to do the sum of from 1 to n of the function 1 divided by r plus 1. So this doesn't look anything like the format that we wanted it, right? Because remember that our format, our desired format for method of differences is to have something that looks like this, right? Or maybe even an f of n minus 1 here. But the point is we want to have a term, its previous term, or its next term to be all in one place. Well, we don't have that here. Well, how can we get that into that format? Well, we're going to have to do something to separate this into two different fractions, right? Well, this is pretty clearly, if you remember your C3 and C4 stuff, this is clearly a partial fraction decomposition function, or a partial fraction decomposition problem, right? Because we know the whole point of partial fraction decomposition was taking a fraction where on the bottom we had a product of two linear factors, or actually in some cases some quadratic factors, and we separated them into two fractions that are either being added together or subtracted together. And our method for doing that was by saying, well, if this can be subdivided into two separate fractions, then they have to have denominators r and r plus 1 respectively. So we would say we have some unknown a over r plus some unknown b over r plus 1. And then we would say, if we were to combine this as one fraction, well, it'd have to be equal to this, right? This is the unique way of representing this fraction without, with ignoring constants over constants. So obviously this here could be 4 over 4r times r plus 1, but we're ignoring any of those constant multiplications that we could do. So combining the fractions here, we would get a times r plus 1 plus b times r, all divided by r times r plus 1. And then we can clearly see here that if these are the same, well, then the numerators have to be equal as well. So we'd have to have 1 equal to a r plus 1 plus br. And this, can be solved in various different ways. But the best way, in my opinion, you could expand this and compare coefficients and get a system of equations, so on and so forth. My favorite way of doing it is by just picking convenient values of r. Because remember, these a's and b's have to be true for all r. So let's pick r is equal to minus 1. What happens when r is equal to minus 1? Well, this entire term disappears here, right? So we'd be left with 1 is equal to just, well, minus 1 times b, so minus b, which means b is equal to minus 1, right? And let's pick r equal to 0. Well, when r is equal to 0, this term dies out, and we're left with just, well, 1 is equal to a. Great. Okay, so now we've got our partial fraction decomposition. We can now say that 1 divided by r times r plus 1 is equal to 1 divided by r minus 1 divided by r plus 1. Great. So this is good, because if we look at this, we can now say, well, this is in our format here, right? Our function of r is going to be 1 over r, and then that means that this thing can be written as f of r minus f of r plus 1. So we're all good. I'm going to move over to this side of the page here, because it should be able to fit up here. So let's try and just go through it. We've got the sum now of 1 over r minus 1 over r plus 1 from 1 to n. Well, let's write out the terms. First term is going to give us 1 divided by 1 minus 1 divided by 1 plus 1 is 2. Next term is going to be 1 over 2 minus 1 over 3, so on and so forth. Second to last term is going to be 1 over n minus 1 plus 1 over n. Last term is going to be 1 over n. Minus. Right. Second to last, our last one is going to be 1 over n minus 1 over n plus 1. So, do our cancellations. 1/2 cancel, the 1/3 cancel, everything in the inside cancels. Our 1 over n minus 1 cancels with our 1 over n minus 1 that would be to the left of it. Our 1 over n cancels with our 1 over n. And what we're left with is just 1 minus 1 over n. In fact, now that I'm thinking about it, I think we did this problem already. I think this was the first example that we did. Doesn't really make a difference, because the important part of this question was this over here, this bulk part. And you will be expected to do some partial fraction decompositions in FP2, but the good thing is they're never gonna, they're never gonna expect you to they're not, well, I should say it this way, they're never gonna give you a partial fraction sequence that you have to sum up that doesn't actually end up coming into the format f of n minus f of n plus 1, which is good, right? Okay, so I think that's actually going to be it for right now. I mean, I could come up with more difficult examples. I could steal some examples from the book, but the basic method has been explained, and this is a really short chapter, just kind of thrown in there to get you ready for the complex numbers section, which is quite a bit more difficult. So, hope it helped. I'll see you next time.